Boom, Julian, welcome. This is Physics 124, and the title is Electromagnetism. Yeah, it's a very broad topic in physics, very wide. It's made up of 13 chapters. It's divided into two. I take electricity part, while energy focuses on the electromagnetic part and modern physics. Well, I think a time will come I will focus on modern part and magnetic field as well. But my major job for today is the electrical part, and the electrical part spans from chapter 1 to chapter 8. You get it? So chapter 1 to chapter 8 is the electrical part of this particular course, Physics 124. And we are going to start with chapter 1, which is electrostatics. Chapter 2 is electric field. Chapter 3 is Gauss law. Chapter 4 is electropotential. Chapter 5 is capacitors. Chapter 6 is dielectric. Chapter 7 is electricity, that's simple circuits. And then the last chapter I'm going to be taking is chapter 8, which is Kirchhoff principle of complex circuits, and potential dividers. So basically that is an overview of what I have to do. So let's start with a very big chapter there, which is chapter 1. All right, so the electric part is electromagnetism. First, let's define what electromagnetism is, okay? Electromagnetism is the study of electric and magnetic field interaction. That means the interaction between electric field and magnetic field is what electromagnetism is all about. But this chapter is going to be focused purely on electrostatics. Yeah, electrostatics. That is what this chapter is focused on. But it cuts the demands to define what electromagnetism means, right? The interaction between electric field and a magnetic field. That gives you electromagnetism. Now, but in the concept of discussing electrostatics, charges are parameters that you cannot do without. You can't talk about electrostatics without charges, okay? Now, charges can either be stationary or moving. They can also be referred to as discrete charges or continuous charges. Discrete in the sense that they are actually in a standard position, they don't move, but continuous in the sense that they are in continuous movement, right? So these charges are of two types. You have positive and you have negative charges, right? Good. Now these charges can actually be viewed by an instrument called an electroscope, and usually they have measurement in Coulomb, okay, represented by C. Now, the study of the interaction of these charges, be it positive, be it negative, be it moving, be it discrete, is referred to as electrostatics. And of course, having understood what electrostatics is all about, the next thing is on the aspect of an atom, because charges actually originate from atoms. You can't talk about charges without mentioning atoms, because charges are subsets of atoms. An atom is regarded as the basic unit entity of any element or any substance, and it is made up of three compulsory charges: the protons that are positive, the electrons that are negative, and the neutrons that have no charge at all. And it's important for you to know that the proton and the neutron contributes to the weight of the atom. In fact, 99% of the weight of an atom is found in the proton and the neutron, right? While the electron happens to be the weightless particle of an atom. Weightless. The mass of a proton is far greater than the mass of an electron. In fact, between proton, neutron, and electron, the neutron happens to be the heaviest particle in an atom, because its mass supersedes the mass of every other particle. The mass of a proton is 1.673 times 10 raised to the power 27 kg. The mass of a neutron is 1.675. You see the difference? 673 for a proton, 675 for a neutron, times 10 raised to the power 27 kg. Now look at that of an electron, 9.109 times 10 raised to the power of minus 31 kg. That's pretty small, bro. You have over 30 zeros before you have 9.103. Meanwhile, the others are in their front zeros, Good. So the mass of the proton and the mass of the neutron are 2,000 times greater than that of an electron. And that is how bad it is. However, take note, the charge of the nucleus of an atom is positively charged, right? Because it contains positively charged protons and neutrons. While the charge of an atom is said to be electrically neutral because of the number of positively charged protons being equal to the number of negatively charged electrons. So you declare that electrically neutral. So that takes us to the principles of charges. There are two basic principles of charges. Number one is the principle of charge conservation. And then number two is the principle of charge quantization. They are two different things. So the principle of charge conservation states that in an isolated system, the sum of all charges equals zero. Equals zero. In an isolated system, add all the charges, both positive, negative, it will give you zero at the end of the day. A typical example of this conservation of charge is experienced in a neutron, when a neutron decays into three particles, which are the proton, the electron, and the neutrino, antineutrino, that's the name, represented by V bar, antineutrino. The charges before and the charges after happens to be equal to zero. And now that takes us to the next guy, which is called the principle of charge quantization. The principle of charge quantization is also defined in a closed system. And what does it state? The principle of charge quantization states that the quantity of charge in an isolated system is the integer multiple of the number of charges in that system, or the number of protons, or the number of electrons in the system. So, principle of charge quantization talk about integer multiple in an isolated system, whole numbers. Purely whole numbers, and has nothing to do with fractions, right? So on that note, Q is equal to NE. E there is 1.6 times 10 to the power minus 19 Coulomb. N is the number of charges, which can be the number of electrons, and usually negatively charged as the case may be, and purely whole numbers. Now that takes us to the concept of quarks. What is a quark? A quark is simply the smallest entity of a particle in an atom. All particles in an atom are made up of very tiny entities, very elementary entities called quarks. I'll give you a typical example. There are two types of quarks. We have up quarks and down quarks. Up quarks are positively charged, while down quarks are negatively charged. As for positive charges, they are 2/3 the charge of an electron, while the down quarks, which are negatively charged, are 1/3 the charge of an electron. And that simply means that if I have to tell you how a proton happens to be positively charged, I will tell you that a proton consists of 2 up quarks and 1 down quark. 2/3 of a charge 2 times plus 1/3 of a charge, which is negative, will give you a positive charge at the end of the day. That is an electron. So that's a proton. As for an electron, it is made up of 3 down quarks. Negative 1/3 of a charge into 3 places will give you a negative charge at the end of the day. And then you may wonder, what is the charge of a neutron? A neutron in terms of quarks is made up of 1 down quark and how many up quarks? 2 down quarks and 1 up quark, so that will give you a total of 0 at the end of the day. And take note, quarks do not exist on isolation. Neither do they exist as whole numbers. Quarks don't exist as whole numbers. They exist as fractions, 1/3 or 2/3 of a charge. And on that note, they do not obey the principle of quantization of charges, but rather I can obey the law of conservation of charges, because they can sum up to 0, and they can sum up to the net charge of the isolated system. So the reason why they don't obey the law of quantization is because they are not integers. They are not integers. The law of quantization says that in an isolated system, the total quantity of charge is the integer multiple. You get the point? So they are not integers, so they cannot obey that law of quantization. And charges are not expected to be in decimals. They're always expected to be in full values, except you are looking for the quantity of quarks, right? All right, so let's go into the next part of it, which is Coulomb's law. Coulomb's law. What does Coulomb's law state? According to Sir Coulomb's, when you have 2 charges separated by a distance r, the force of attraction or repulsion existing between those 2 charges is directly proportional to this product of those 2 charges, but inversely proportional to the square of the separation distance existing between those 2 charges. And that would take you to F being equals to KQQ divided by R squared. And the Q we are talking about are magnitudes. Ignore their charges, whether it's positive or negative. We're looking at the magnitude. So they must be positive at the end of the day. So K there stands for the constant, And the constant we are talking about there is given by 9 times 10 raised to the power 9 Newton meter square per Coulomb square. So K is the constant there, and also depends on the permittivity of the medium. If actually this force exists in free space, then you will talk about K naught. So you will have your K naught inside the formula to become K naught, the magnitude of Q1, Q2 divided by R squared. And take note, the value of K naught is equal to the value of K. 9 times 10 raised to the power 9. They are both equal, right? Now, but one thing you need to understand is the value of K is 1 all over 4 pi epsilon 0 if it is in free space. But if it is not in free space, it's 1 all over 4 pi epsilon. And that value is 9 times 10 raised to the power 9. But the epsilon is 8.85 times 10 raised to the power minus 12, right? So you have to understand this very vividly, and it's very clear. Then another important fact that you should remember is that an electric force, that the electric force that two charges exert obeys the law of Newton's third law. That means the force and the reaction force are equal. That means if I have two identical charges, the force each one will exert on the other are equal. The reaction each one will exert on the other are equal. No one will be greater than the other. Why? Because they are identical charges. They have the same capacity of quantity of charge, and they have the same directional pull. So it must give you equal. That's what you have to take note of. Then that takes us to the law of superposition principle. And the law of superposition principle states that when you have multiple charges surrounding a particular single charge, the force net acting on that single charge is the algebraic sum of all the forces on that charge. I don't know if you get the message. The algebraic sum of all the charges, or of all the forces acting on that charge. Let's say Q1 is surrounded by 5 charges. Now, the force of attraction between, or repulsion between Q1 and Q2, that's 1F. Then the second one is the force of attraction between Q1 and Q3. The next one is Q1 and Q4. The next one is Q1 and Q5. The next one is Q1 and Q6. So the algebraic sum of the forces of attraction will give you the net force, and that's superposition principle. And of course, the separation distance is still between the charge in question and the ones that are surrounding it. So you will always have to play that game and get the superposition part of it well done. Now that takes us to a dielectric medium. In a dielectric medium, the relative permittivity, ER, is defined as the ratio of the permittivity of the medium to that of free space. Permittivity of the medium to that of free space. That means ER is equal to epsilon all over epsilon naught. So if you make epsilon the subject of the formula, you have epsilon R times epsilon naught. And if you write the formula of K to be 1 all over 4 pi epsilon, and K naught to be 1 all over 4 pi epsilon naught epsilon R. In other words, we are not dealing with it in a medium where there is permittivity. That means your epsilon changes to epsilon naught epsilon R. And if you curve out 1 all over 4 pi epsilon naught, which is K naught, and substitute there, you are going to have epsilon R, making it the subject of the formula, to be the reverse of epsilon over epsilon naught. So that gives you K naught all over K. So that is a relationship between relative permittivity and the constants in Coulomb's law, right? Very, very important parameters that you shouldn't forget. These parameters are very, very, very key. Now that takes us to two charges. Two charges positioned at an angle, not really an angle, but let's say they are positioned in two places such that you have a right angle between them. One is at the top, one is at the bottom, so they can form a right angle triangle. The distance between them becomes a hypotenuse. So if you're asked to calculate a force existing between both of them, it's simply through Pythagoras theorem, you get a hypotenuse, and once you have the hypotenuse, that hypotenuse will help you calculate the force of attraction or repulsion existing between those two charges. Now, in some chronic cases, you'll be asked to calculate the individual force exerted by one. F1, what is the magnitude of the force of F1? F2, what is the magnitude of the force of F2? Now, the gospel truth about it is that because they are identical charges, F1 and F2 are equal in magnitude. We have said that before. They obey the law of Newton's third law. However, if you must do these calculations yourself, then you will have to analyze each of these charges with respect to a three-dimensional diagram so as to form a right-angle triangle. And the angle will always be focused on where the charge is. The guy at the bottom will have his field lines radiating outward, of course, going in the hypotenuse direction, while the other one is going towards the negative x-axis, while the vertical one goes towards the positive x-axis. So you will have a sum of your F1 force to be minus Fx. Why? Because it's going to the negative x direction, and plus F1y, meaning it's going to the positive y direction. So as for F2 that is at the top, one radiating towards the hypotenuse, the other one radiates towards the negative y-axis, the other one radiates towards the positive x-axis. So you're going to have your F2 to be F2x minus F2y, as the case may be. So for you to calculate the values of F1x and F2x is simply F1 sine theta, and then F2 is F2 cos theta, as the case may be. So through those triangles, you can just look for cos theta, sine theta, and boom, you're good to go. Just remember, positive charges radiate their field lines outside. Negative charges radiate their field lines inwardly. Very, very important. Now, that takes us to three charges standing on the same line, and you're asked to calculate the net force on a particular charge. Let's say I have three charges, a negative Q1, a negative Q2, a positive Q2, and a negative Q3. So what do you think will happen? One is negative, the middle one is positive, the one at the other extreme is negative, and you are asked to calculate the force exerted on Q1. The gospel truth about it is that Q1 that is negatively charged and Q2 that is positively charged will experience a force of attraction, while Q1 that is negative and Q3 that is also negative will experience a force of repulsion. However, because Q2 is closer to Q1 than Q3, Q2 will have a higher force of attraction than the repulsive force coming from Q3, because Q3 is very far away to Q1. So on that note, you have to resolve the forces of attraction. The force on 1 as a result of 3 will be going towards the negative x-axis, while the force on 1 as a result of 2 will be going towards the positive x-axis. At the end of the day, you find the difference between the forces. And of course, finding the difference between the forces is the bigger force minus the smaller force, so that you have a positive result at the end of the day. All right. Another fact that you must take note of is when two equal charges are separated by a thread at a common point, such that they repel each other at a distance of r, making an angle of theta to the vertical, then it is important for you to know that the separation distance existing between both of them can be calculated using sine rule. Yeah, you have to do the diagram. You have two balls on two threads. Because they are repulsive, because they have the same charges which are positive, they repel each other, and the distance between them is r. The angle formed at the top of the point where it is clocked on the wall is theta, and that same angle is also the same on the other side. So for you to calculate using sine rule to get r is the distance between them, the length of the thread at the two opposite sides, while the angle between them is 2 theta. Then the angles at the bottom are alpha, alpha. They have to be equal. In other words, it's going to form a scaling triangle from the within. And from there, you can make your r the subject of the formula using sine rule. And that is the length divided by sine alpha being equals to the radius divided by sine 2 alpha. 2 theta, And you make r the subject of the formula, and you will just be good to go. Then, if you are asked to calculate the force exerted by these charges, the force exerted by these charges actually moves in the opposite direction. As they repel each other, the forces are moving in the x and negative y direction. So the magnitude of that force can be determined using Lami's theory. And of course, the bedrock of this is determining the value of theta, which is the angle between the weight acting downward and the thread that continues. Now that thread that continues in between the force and the magnitude of and the weight is theta. that theta is in alternate angle with theta that is up. So from there you can just do your mago jigidi and get the 3 angles for the 3-dimensional stuff and apply still sine rule, which is in quote Lamar's theory, which is now F, which is the force, all over the angle opposite it. Then T, there is a tension, no longer the length. T is tension now, all over the angle opposite it, and then the weight all over the angle opposite it. That's Lamar's theory, right? Next is the charge on a particle. Of course, if you are given 2 charges, or you are given a particular identical charge, you are given the force existing between them and the distance between them, and you ask to calculate the quantity of charge, just make you the subject of the formula. And you will just be good to go. Now take note, when the electrostatic force of attraction between 2 charges happen to be equal, the weight happen to be equal to the weight of another particle, then the force using Coulomb's law is equal to mg. And that simply means that K0 Q1 Q2 all over R squared is equal to mg, right? So very, very important. You have to take note of that. Also note, when you have 3 charges that are positioned at right angle to each other, that means 1, 2, 3 forming a right angle, Q1 at the middle, Q2 up, Y, Q3 by the right. And then it's important for you to know that if you're asked to calculate the force on this one or the other, look for the attractive force, look for the repulsive force, take the directions. If it is positive x and negative y, then get the values and then calculate for the angle of theta, you know, stuff like that. Resultant force, those are simple things and you can do with them accordingly. So that is the end of this chapter. Chapter 1 is done and dusted, and we're meeting again in chapter 2, and that is electric field. Boom. All right, ladies and gentlemen, to get to quintessence tutorials, you need to follow 3 steps. Number 1 is to get to Unibend's second gate. Okay, this is Unibend's second gate. The next thing to do is to cross the road. And of course, there is a net, so we have to follow this way by the right. If you follow this way, it will take you to Unibend main gate by the bridge. But you follow your right to the end of the road divider. Now we are at the end of the road divider, so you can cross the road from here. So once you cross the road, the next thing you are going to see is 24th Street Junction. Okay, you will see this 2-story building, that is Odaro Plaza, and if you look over there, that's Quintessence Tutorials banner. Okay, so this is the street you walk down. At the end of this street, just by the blue gate you see at the end over there, that blue gate after the tree, that's Quintessence. So by the junction, you will see the Soft Touch Hotel, you will see Coulomb Group of Schools. So walk down the street. Next, you will see Coulomb Schools. Yeah, that's my school there. Then just after the school, you see Quintessence. At this point, facing you is Believers World, okay, Christ Embassy. Then if you look by your right, you will see Welcome to Quintessence Tutorials. Oh yes, that's the venue. Hope to see you shortly.